Okay, so let's kind of do a small recap. We were talking about having the uh, finite size uh, and nuclear spin effects on the spectrum of hydrogen-like atoms, and uh, uh, and what we said was that like nucleus can be written in terms of its constituents, but it really does not matter for us as far as atomic physics problems are concerned. Only thing that is important for us is that the strong interactions between protons and neutrons preserve the rotational invariance, and therefore the nuclear Hamiltonian would have rotational invariance, and there must be a nuclear angular momentum which we call I, and that I should commute with the nuclear Hamiltonian. Okay. And of course, since I is also an angular momentum algebra, it should satisfy the angular momentum um, commutation relation, which is I j is equal to I epsilon I j k I k. Of course, nuclear angular momentum has nothing to do with the electronic angular momentum, and therefore these commutation relations just vanish. Okay, the nuclear angular momentum with orbital as well as spin angular momentum of electrons. Okay, given that Hamiltonian commutes with I, nuclear Hamiltonian commutes with I, the nuclear eigenstates could be written in terms of simultaneous eigenstates of energy as well as eigenstates of I squared and Iz. Okay, so one could kind of classify the spectrum of nuclear Hamiltonian, but that is not our concern because the energies involved in nuclear physics are much higher than the energies involved in atomic physics, and therefore we would really be interested in nuclear ground state. Okay. Now, the fact that we are interested in nuclear ground state does not necessarily mean that the ground state has to have I is equal to 0, simply because I is a complicated combination of orbital angular momenta of all the protons and neutrons constituting the nucleus, as well as the spin angular momenta of individual protons and neutrons undergoing a vector addition. So how how a specific value of I is arrived at is not our concern. All that we need to know is what is the value of I. And in fact, throughout our atomic physics computation, we are going to treat I as a fixed number because it is just angular momentum of nuclear ground state. Okay, and it is not going to be a variable, unlike L and S. Well, not even S, but unlike L, which kind of keeps changing depending upon which state you are looking at. S is of course going to be half as long as we consider only a single electron state. Okay, fine. So this is something we had discussed last time, and as I was saying that the ground state must be an eigenstate of I squared as well as Iz, and with eigenvalues I into I plus 1 and Mi. Okay, fine. So now what we want to do is basically study a combined system because under the spatial rotation, the total angular momentum of the system is what is important. Within the nuclear physics problem, of course, the nuclear eigenstates are since we are looking at only ground state, would be a 2i plus 1 fold degenerate, and and if you look at the combined electron and nuclear system, then we would be writing the corresponding state as electronic state written in terms of principal quantum number, the orbital angular momentum, spin, total electronic angular momentum, and its projection. Okay, times the nuclear state, which is written in terms of I and Mi. Okay, and this state is of course 2 times 2j plus 1 times 2i plus 1 full degenerate if j is less than n minus 3 by 2, and when j is n minus half, then the degeneracy is half of that. Okay, this is something we already knew. The first two factors, 2i plus 1, just go for a ride in this particular case. Okay, now remember both electron and nucleus have magnetic moments because both electron and the constituents of nucleus carries spin degree of freedom, and that is the one which leads to magnetic moment. And the best way of seeing that is to turn the external weak magnetic field and see how the spectrum of the nuclear Hamiltonian changes. Okay, now of course, what happens is that the nuclear Hamiltonian would be shifted by the external magnetic field times its magnetic moment. If nucleus did not have magnetic moment, then it would not have affected the spectrum. So what you do is you turn it on and check whether the spectrum changes, and indeed, of course, generically you find that the spectrum does change, and so therefore, based on that, you assign a magnetic moment to a nucleus. Now, of course, it depends upon how many nucleons are there in a nucleus that this magnetic moment would kind of change. If we are looking at only a hydrogen atom, for example, then it is only a proton, and it is a proton magnetic moment which will sit out there. Okay, so okay, so what we'll do is we'll write the nuclear magnetic moment in terms of the proton magnetic moment, which is E upon 2mp, where mp is proton mass, times the nuclear angular momentum, times factor GL. This Landé-G factor is 2, for example, for the electron, but here this is some kind of order 1 number, which kind of depends on what is the effective term coming from vector addition of all nucleons in the system. Okay, so and we don't really need to know this number very accurately, as long as this number is roughly of order 1. Okay. Fine. Now, on the other hand, if you look at the magnetic moment of the electron, that is something we know, and that is written by the in terms of the Landé-G factor times the electronic magnetic moment, which is E upon 2 times mass of the electron times L plus 2s. Okay, so this is this doubling of the Landé-G factor for the electron. Okay, so that is something we had done earlier. Okay. Okay, so so the reason why we are not kind of getting into too much details of exactly how the factor comes about and how I is defined is simply because even in case of electron, we had understood that, like, this is not directly proportional to J, but it is J plus S, this thing. Given that the nuclear magnetic moment is a vector sum of the magnetic moments of every nucleon, it's going to be too much to kind of actually determine how the whole stuff is going to be written down. Okay, so therefore we kind of don't worry about that detail. Okay, but what we will basically be doing is just concentrate on only the ground state and claim that in case of the ground state, the nuclear magnetic moment of the ground state is proportional to the nuclear angular momentum of it. Okay, and so we will not get into how the nucleus behaves when the system becomes excited, simply because if the system is excited, then there are additional orbital angular momentum contribution between various nucleons, the relative motion between them, all of that could contribute to it, but it is not our concern because we are only looking at the ground state. Okay, fine. So this assumption is reasonable as long as we are doing atomic physics. This assumption is not reasonable if you are doing nuclear physics, because you will have to look at entire spectrum. It's like solving quantum mechanics for nucleus. Okay, but that's not our problem right now. Okay, fine. Okay, so to understand like validity of this assumption, let's try to kind of look at a matrix element of the nuclear magnetic moment in the nuclear eigenstates. Nuclear eigenstates are, of course, written in terms of the energy eigenvalue times and other simultaneously diagonalizable quantities. I'm not writing down energy eigenvalue simply because we are essentially working with the ground state, so it is the same state that we are going to look at all the time. Okay, so this matrix element is of course going to be just GL times the nuclear magnetic moment times the expectation value of I within these states. Okay. So now to show that the left hand side and right hand side have same mi and mi prime dependence, what we will do is we'll use the Wigner-Eckart theorem. I suppose you must have done Wigner-Eckart theorem in QM1, right? Hello?
I don't, but I personally don't remember it by any name.
I see.
No, we did.
There's a
You,
Wigner-Eckart theorem in representation theory.
yeah, angular momentum algebra. Yeah, in representation theory in general, of course, yes. But what we need is really only the angular momentum algebra Wigner-Eckart theorem. You can do it for arbitrary algebra. It's kind of same rule, this thing, but it's much simpler for angular momentum algebra. I suppose I must have been done when you studied angular momentum algebra, but if not, you please let me know.
I mean, if you start, we can see.
Okay, because we will be using Wigner-Eckart theorem like quite often actually. So that's why it would be useful to know whether it is done or not. And if it is not done, then I will have to give the lecture today for sure. But what I can do is that on Saturday, if you are meeting, then I will actually take up Wigner-Eckart theorem first. Okay, it is like, it will take about an hour to figure this out, this thing. But I would like to know what others think. I mean, others means everybody, in fact. I wish people speak up.
No, actually, it is not done. It was not done.
It was not done.
Yes, it was there in the syllabus, but it was not done.
Of course, it is there in the syllabus.
I mean, we did do the Clebsch-Gordan coefficients, but
Yeah,
is
yeah.
that what you're talking about?
No, Clebsch-Gordan coefficient is part of the theorem, but there is something called a reduced matrix element that you need to kind of. So you relate a particular computation to be equal to Clebsch-Gordan coefficient times the reduced matrix element, and the reduced matrix element does not depend on magnetic quantum numbers. So that is the kind of stuff. So we are going to use those tricks over and over again, actually. So. So yes, Clebsch-Gordan of course is part of the Wigner-Eckart theorem, but they are there whenever you go from LSJM basis to MLMS basis, you need Clebsch-Gordan basically. Okay, let's see. Let's go ahead and let me kind of say a few things and see if you can. I mean, if you have done this in the course, then it is good. If not, then we'll kind of take it up. Okay. Does that sound okay?
Yeah.
Okay. Okay, so what we are going to do is to use Wigner-Eckart theorem to show that both sides of this equation have same dependence on mi and mi prime. Okay, so so in the Wigner-Eckart theorem, what basically we'll be using is the fact that both the nuclear magnetic moment quantity and the nuclear angular momentum, both of them are vectors. Okay, so these are kind of with respect to angular momentum algebra, they are vector quantities. Typically, you can define something called tensor operators. So there exists a class of operators which do not transform under rotation, which we will call scalars. There are class of operators which transform like a vector. They are called vector operators. And then there are operators which transform like second rank tensor, third rank tensor, and so on. So generically, you write down tensor operators. You may find some books calling it spherical tensors, whatever. But in this particular case, we just have a vector. Okay, both Mn and I are vector, and you can write them as Mn1, Mn0, and Mn-1 in terms of their x, y, and z components in this particular form. This is pretty much like the way we had written L plus L minus and L0 in case of angular momentum algebra, orbital angular momentum algebra, or similarly for spins and so on. So this operator also could be written in this particular form, Mn 1, 0, and -1. And same, of course, would be for the nuclear angular momentum. So it would also be written as I1, I0, and I-1, written as Ix plus Iy, Iz, and Ix minus Iy, up to some normalization. Okay. Now, Wigner-Eckhart theorem tells us the following thing. It tells us that if you are trying to compute a matrix element of a spherical tensor, in this particular case, of course, we are looking at only a vector quantity. If you are computing that a matrix element, then that matrix element is written in terms of the Clebsch-Gordon coefficient times the reduced matrix element of that operator in the states where the magnetic projection of that state is not important. Okay, so notice you have ML here, sorry, MI written here and MI prime written here, but this double line matrix element, which is called a reduced matrix element, is independent of what MI and MI prime you choose. Okay, and all the dependence of MI and MI prime is sitting inside this Clebsch-Gordon coefficient. Okay, remember both the states have same value of I, so therefore Clebsch-Gordon coefficient is I1 I. This factor is 1 because the operator that we have sandwiched is a vector operator, which is spin 1, okay, or angular momentum 1. Okay, but this statement is nothing special about the vector operator. You could have inserted any tensor operator there. So, for example, you could have inserted a third rank tensor operator, then it would have been I3I. Okay, that would be the expression. Okay, so now, of course, we are looking at a specific matrix element. You could have looked at some I prime and I also, and then sandwich something else. But that is a different kind of matrix element. Okay, so we are looking at a very specific kind of matrix element where the I eigenvalue is not changing, only its magnetic projection could change. And the reason why we are doing this is because as far as our problem is concerned, the nuclear angular momentum is not going to change because its ground state is fixed, whose angular momentum is a fixed number for us. Okay, and it's not a variable, which is what I was saying some time ago. Okay, so that is the reason why we are computing it in the same I value, but magnetic projection could be different. Okay, and the Wigner-Eckhart theorem tells us that this matrix element factorizes into the Clebsch-Gordon coefficient times the reduced matrix element. And this statement is true for any other vector operator, because this is a statement about tensor operators in angular momentum algebra, nothing to do with what is the precise form of that tensor operator. Okay, so therefore, if this statement is true for Mn, it is also true for I. Okay, and it tells you this. Okay, Clebsch-Gordon coefficient, if you can recall, has the property that it is non-zero only when M plus Mi prime is equal to Mi. Okay, so if Mi is exactly the sum of this M and this Mi prime, then only this matrix element would be non-zero. Otherwise, the matrix element would just vanish. Okay, now of course, besides that, this angular momentum addition also needs to work in the sense that, like, in our case, it is kind of easy because I1 does factorize into I, but you may have something like I plus 3, 1 I, and that of course clearly wouldn't factorize. So Clebsch-Gordon coefficient has two conditions. The lower components, lower indices have a property that the first index is the sum of the second and third, and the upper indices have the property that the angular momentum algebra has to contain the first index in the product rule of, or angular momentum addition rule for the second and third. Okay, and that of course is true in our case for the upper case. The lower case is a condition that we need to impose. Okay, fine. So what we can do therefore is that you can compare these equations and you can write down the matrix element for Mn, okay, in the nuclear states with different magnetic quantum number as a reduced matrix element for Mn times the matrix element for Im divided by the reduced matrix element of I. Okay. Does it make sense? All I have done is basically replace the Clebsch-Gordon coefficient in the first equation here by matrix element of Im divided by reduced matrix element of I, because this Clebsch-Gordon is same as that Clebsch-Gordon. Okay, so therefore I just remove the Clebsch-Gordon and write down the matrix element for the components of nuclear magnetic moment in terms of matrix elements for the components of the nuclear spin multiplied by the ratio of two reduced matrix elements. Okay, one of them is the reduced matrix element for the nuclear magnetic moment divided by the reduced matrix element for the nuclear angular momentum. Okay, so this is kind of a straightforward manipulation. What is required is to understand that the Wigner-Eckart theorem tells you this. Okay, if you remember this equation, then the next step actually follows. Okay, if you have not seen this equation, then you may have to derive it at some point. Okay, does it sound okay?
Sir?
Yes.
This this term, the first one, L was like L mi was no m square L any state which has a total angular momentum L is an eigenstate of this mn square. Sorry.
Mn square? No, not necessarily.
Summation of mx square plus my square plus mz square.
Yeah. Well, if you write it in this particular form, if you write Mn in this particular form, yes, it is true. Yeah.
Yeah. So like what I'm saying is this should be non-zero only when both L's are same.
No. No. So this is just angular momentum addition rule, right? You write down a tensor operator, okay? Then it tells you that if you have some angular momentum, tensor operator angular momentum, then the value. So suppose this is a tensor operator with rank say j, okay? Then the state here, which would give you non-zero answer, is if the value written here, this let's call this value I prime, then I prime is I plus j minus 1, I plus j minus 2, dot, all the way up to mod of I minus j. Okay.
Yeah.
All those values sitting on this side are allowed. Okay.
Okay, so it depends on the rank of the tensor.
Yeah, it depends on the rank of the tensor, absolutely. So in this particular case, it is 1. So it is I plus 1, I and I minus 1. All are allowed on this side. Okay. We are not looking at all other eigenvalues because all other states, simply because we have decided that we are going to look at only nuclear ground state with a fixed value of I. Okay, that is why matrix element between the same I state. Okay, otherwise it's angular momentum algebra rule between this tensor operator and this state. Okay.
Yeah.
Fine. So what we have done is we have traded off the computation of the matrix element of Mn to computation of matrix element of the nuclear angular momentum up to a ratio of reduced matrix elements. Okay, and the reduced matrix elements have the property that they are independent of the magnetic projections. Okay, simply because this reduced matrix element by definition does not depend on m and m prime values. Okay. So what we will do is we will basically identify this quantity, which is independent of m and m prime, to be just GL times mu n. Okay, and if you do that, then you basically recover this relation. Okay, the relation between the magnetic moment and the nuclear angular momentum. Okay, and this is purely done. Yes.
Mn was defined as Gi mu n I, right?
No, no, no. I said I wrote that first, and then I showed you that through. Yeah. So what I'm saying is that then that this expression can be derived, okay, by actually showing that. See, okay. So let me go back. Go to this step. See, the dependence of the nuclear magnetic moment on I is not so easy actually. Okay, it's a complicated expression. We choose this for the ground state because we just say that like okay that we have a state with fixed nuclear angular momentum, and we are not going to look at anything any other nuclear state. Okay, how the arbitrary state nuclear magnetic moment depends on I is something that we don't know. Like for example, even in case of electron, it is not just a function of J, but it is J plus S. So it may be a complicated function of I and some other kind of effective spin quantum number of nuclear system. We don't want to even look at it. Okay, so what I wanted to establish was that this expression that we had written down, okay, for the ground state, okay, makes sense provided you do not worry about any other nuclear degrees of freedom. Okay, so that is what we basically established. Okay, Mn for a generic state could be a very complicated object. We don't even know what it is. Okay, and we don't even need to know what it is actually. Okay.
So, well, like what we are trying to say is that regardless of whatever state the nucleus is in, which is characterized somewhat by Mi and Mi prime, like we can still write this.
Yeah, no, only ground state. Okay, regardless of what form the ground state takes, if you assign a specific angular moment to that momentum to that state, which you can because the nuclear Hamiltonian commutes with angular momentum, then it can have different magnetic projection, but it has a fixed angular momentum. And in that state, Mn can be replaced in terms of I. Okay. But if you look at excited state, then Mn may not be I. It may be I plus some additional effective spin generated by various nucleons. And we don't know what that is. Okay.
Yeah, okay.
Yeah. Fine. So this statement basically makes sense only for the nuclear ground state. Okay. Arbitrary excited state, this formula we may have to really modify. There may be additional factors, but we don't care about that because our problem concern has only nuclear ground state in our mind. We are not going to use anything else.
So,
Okay.
so this, yeah.
Yes.
So this requires the magnetic moment operator also to commute with the Hamiltonian.
Magnetic moment operator to commute with the Hamiltonian?
Yeah.
Where in the nuclear case?
Yeah.
Yeah, of course it does.
Yeah.
Okay. So because that magnetic moment operator is written in terms of combination of the angular momentum operators. But every angular momentum operator commutes with the nuclear Hamiltonian. So therefore it would commute. Okay. But it's just that like what is the combination? Is it L plus S or is it L plus 2S or it is the way in case of electron? There also it could be I plus kind of combination of various vector additions of the spins of the nuclei. We don't know. Okay. But we don't need to know. That is a statement that we are trying to make.
Okay. Yeah.
If you are looking at the entire spectrum, then we would be in a big mess. Okay, but we are not looking. We are looking at one particular state and just do a computation using that state all the time. Okay. Okay. So now the point here is that like if once you have obtained a nuclear magnetic moment operator, then clearly it would generate some magnetic field, and that magnetic field would be seen by the electron, and we would have to ask a question that what is the nuclear magnetic moment does to the electronic states. Okay. So clearly, if you have a magnetic moment, it would produce a new vector potential. Remember, originally when we solved the problem, our problem was basically just p squared upon 2m plus the Coulomb potential. That is what the Schrodinger equation was. We solved that problem, but now if you take nuclear magnetic moment into account, then it is not p squared over 2m, but p minus e by c times a, where you can substitute this a coming from the nuclear magnetic moment as a vector potential. Of course, you can expand that. This quantity is going to be small. You can try to treat that perturbatively. The reason why this quantity is small, because the electronic magnetic moment is proportional to 1 over electron mass, whereas nuclear magnetic moment is proportional to 1 over proton mass, which is like 1836 times larger than electron mass. Okay, so therefore the magnetic moment for the nucleus is very small. Even if nucleus has high angular momentum, nucleus is in a high angular momentum state, say ground state has angular momentum, say 20, it doesn't matter, because some number of the order of 20, 30 or something is not going to affect, because the overall factor is like 2000 sitting in the denominator relative to the electronic magnetic moment. So therefore, this factor is actually small, but nevertheless, we can take that into account to find out how it will split the states. Okay, fine. So the next few lines are just kind of trivial statements that if you want to understand how you get an expression like this, you can think of a dipole as a current carrying coil and try to take the radius of the coil to 0, holding the dipole moment fixed, and then kind of determine A by looking at the magnetic moment, magnetic field generated by current carrying coil, and invert that in terms of the gauge field. Okay, so you have the current, you can figure out magnetic field, and once you get magnetic field, you can figure out gauge field, and you can derive this formula by doing this kind of stuff. Okay, yeah, fine. So what we need to do now is to replace our original equation, which was just p squared by 2m times e plus e times a naught by pi squared, which is p minus e by c times a whole squared, and of course include the coupling of the magnetic field with the electron spin. Okay, the factor of 2 is of course this Landau-G factor for the electron, so you get a factor like that. Okay, so what we'll do is we'll expand this, and we'll kind of ignore the term which is quadratic in A, because as I said that A already is kind of down by a factor of 2000. A squared will be down by a factor of like 4 million. So you can kind of happily ignore that factor and just keep terms which are up to linear in A. Okay, so yeah, this is just the same statement that nuclear magnetic moment is much smaller. Okay, fine. So if you do that, then what you need to do is basically just expand, and then I kind of replace p by minus I h bar times del. Probably I have not even taken care of h bars, probably minus I times del, and then you get an equation which is like this, that h psi is equal to the usual kinetic term plus the Coulomb piece plus this piece. Okay, so this piece comes from the following thing, that when you act this on psi, you write this as an operator p minus e by c times a multiplied by p minus a by c times a. So once p is on the right of a, once p is on the left of a, and therefore you get an expression like this. When p is on the right, you get a dot grad, but when p is on the left, then you get divergence of a times psi. Okay, so those are the two terms, and then there is a term which is proportional to a squared, which we are going to ignore. This piece, I should have put a plus sign here, I forgot. Okay, this sign, there should be a plus sign here. Okay, this is just the magnetic field coupled to the scalar. Okay, so we can kind of simplify this a bit. We can take this divergence acting on a once and acting on psi once. When it acts on psi, it just adds to this term, and you get an expression which is like this. Okay, so you have del dot A piece and A dot del acting on psi with a factor 2. Okay, fine. So so now what we are going to do is that, remember, if you set vector potential to 0, then that was the original hydrogen atom problem that we solved. Okay, so what we are going to say is that this Hamiltonian that we have written down can be written as various terms. The first two terms will be treated as unperturbed Hamiltonian, which is the original one which we solved exactly, and then remaining terms, which are due to the nuclear magnetic field, will be treated as perturbations. Okay, so now there is of course one small thing that one needs to worry about, which we are not actually going to worry about, and I'll explain why. And that is that we write down A naught as a Coulomb potential generated by a point charge. Okay, so whatever, maybe Z times E or some such thing, and we just write down that Coulomb potential, which is a Coulomb potential generated by a monopole charge. Now, if you say that nucleus has finite size and the nucleons are kind of protons and neutrons distributed inside that finite size object in an arbitrary manner, then you should actually interpret that as a charge distribution. And if you interpret that as a charge distribution, then A naught itself should be expanded in a multiple expansion. And in that multiple expansion, the leading monopole term is the one which is actually the piece that is used in solving the Schrodinger equation. And then there are higher multiples of A naught, which should be treated as perturbed Hamiltonian. Okay, although we will not do that because those terms would become relevant only when electron is close to the nucleus. Okay, if electron is like 4-5 orders of magnitude distance away from nucleus, then to a reasonable order, it is sufficient to assume that the monopole contribution to A naught is much more dominant than dipolar and multiple and quadrupolar contributions. Okay, and we will of course work with that assumption. If we find that it is not going to work, then of course we will try to ask what is the dipolar contribution to the Coulomb potential and see whether that corrects our result compared to the experimental data. Okay, so that is the kind of approach. Yes.
Yesterday, like last class, you made a statement on what we mean by spherical symmetry of the nucleus.
Yes.
Like you said that.
No, I said.
Hamiltonian, yeah.
I said the Hamiltonian is invariant under rotation.
Yeah,
Hamiltonian
but that distribution need not be spherical.
That is right. So Hamiltonian having a spherical symmetry does not mean that the state should have a spherical symmetry, right?
Yeah.
So there are two different things. For example, think about a quantum mechanics problem where you have say double well potential. Okay.
Yeah.
Okay. So the double well potential is like V of x is equal to minus x squared plus x to the 4. Okay. So,
even function.
Yeah, it's an even function, simple double well thing. Okay. Now this even potential has a property that x going to minus x is a symmetry. Okay.
Yes.
But if you look at this potential, it has two minima. Okay. So let's call these two values of these two minima to be plus a and minus a, because the potential is even. The minima are symmetrically arranged. Now once you choose one particular minimum, suppose you choose plus a as a minimum, then the state which describes plus a minimum, okay, that state is not symmetric under x going to minus x, because under x going to minus x, you would actually go from plus a minimum state to minus a minimum state, which is a different state altogether. Okay, so therefore Hamiltonian having a symmetry does not necessarily mean that the corresponding eigenstate should have a symmetry. Okay, even in ordinary hydrogen atom problem, that your Hamiltonian has a rotational invariance, Okay, but that does not mean that the states are rotationally invariant. For example, S wave states are spherically symmetric and therefore rotationally invariant, but P wave, D wave states are not actually. Okay, so so symmetry of the Hamiltonian just tells you as to how you will organize the spectrum in terms of representation of that symmetry. Okay, but it does not say that like because the Hamiltonian is symmetric under that, all the states should also be invariant under that. That's not true. Okay.
Yeah.
Okay. Fine. So therefore, there could be a charge distribution, and in fact, like even for the nuclear problem, that the Hamiltonian is rotationally invariant does not necessarily mean that even nuclear ground state would be rotationally invariant. It may not be actually. In fact, that is why we are assuming that it carries some angular momentum I, right? So there are two different statements, that this problem has a symmetry, whereas the solution has a symmetry. In fact, it is an important statement as you would go ahead when you start doing quantum field theory, that or even in advanced atomic, we will see that the Lagrangian having a symmetry and a vacuum not having a symmetry has an important physical effect. Okay, both in critical phenomena as well as in quantum field theory. Okay. Okay. Yeah. So as I said, that although it would be it should be really treated as a multiple expansion by assuming some charge distribution, we really ignore this detail. Okay, because that would be a much more complicated computation and most probably not relevant for electron which is not able to resolve the charge distribution of the nucleus. Okay, so in other words, what we are doing is assuming that nucleus is actually a uniform spherical charge distribution. Okay, and in that case, the vector potential generated by the nuclear magnetic moment can be written in this particular form. This is just using the fact that the cross product can be written in terms of epsilon tensor. Okay, what we are going to do is we'll use this in our Schrodinger equation. Okay, so this is our Schrodinger equation. So we'll substitute A to be this quantity. Okay, good. So first thing to notice is that like if you try to take the divergence of this vector potential, then it's kind of easy to see that that would vanish. Okay, and the reason why this would vanish is interesting, because what we are doing is the following: that we are writing this vector potential which is generated. This is a vector potential which is generated by the nuclear magnetic moment, but experienced by the electron. Okay, right? That is why it is in the electronic problem in quantum mechanics. Okay, so although this expression is written in this particular form, the Mn piece carries information about nucleus, whereas this R object and this divergence or gradient piece, which is a derivative taken with respect to electronic coordinates. Okay, so therefore, when you take divergence of A, it is taken with respect to electronic coordinates, and therefore that derivative actually just runs through Mn and acts on 1 over R. Okay, Mn is written, if it is a distribution and it is written in terms of nuclear variables, then those nuclear variables have nothing to do with the electronic variables. Okay, and therefore this derivative actually only acts on R. Now, when it acts on R, then you have a partial derivative with respect to K, Xk and Xm acting on R with a epsilon KLM, which clearly tells you that this is antisymmetric and this is symmetric, and therefore it should just vanish. Okay, so it is good for us because that is equivalent to saying that we could work in del dot A equals 0 gauge in this particular case, which is what we call Coulomb gauge, and that would simplify our expression, because remember we had a term del dot A times psi sitting around here, and we can happily set that term to 0. Okay, so that leaves us with our Hamiltonian to have unperturbed Hamiltonian, which is exactly soluble, and there are two other terms, which is A dot del acting on psi with a factor of 2, and then there's a del cross S dot S term acting on psi, okay, which is the coupling of magnetic field with the spin. Okay, so what we are going to do is to kind of systematically manipulate these terms and see what terms that we get. Okay, and we'll manipulate those terms in next lecture, hopefully. Okay, so what we are going to do is that yeah, so this is what I was explaining, that the derivative doesn't act on Mn because it is written in terms of different set of coordinates. Okay, fine. So we are going to write down H in terms of H0 plus H1 plus H2. H0 is a problem which is exactly solved already. Okay, so we just kind of write it there. And what we are going to do is to treat H1 and H2 as perturbations. And therefore, with respect to H0, whatever are the eigenstates that we have obtained, we are going to use those eigenstates to compute matrix elements of these perturbations. Okay, but before we do that, we already know what is A, written in terms of nuclear magnetic moment and electronic coordinate R. So we will substitute that and try to kind of massage this expression and try to bring that into a nicer form. Okay, nice, by nicer I mean into a form which is familiar to us. Okay. Okay, any questions at this point?
Sir, Lagrangian having a symmetry and the solution not is this is spontaneous symmetry breaking, right?
Yes, yes, it is spontaneous symmetry breaking.
But usually it is not there, right?
Oh, that is for the ground state, no?
Yeah.
That ground state not obeying the symmetry is called spontaneous symmetry breaking. Yes.
No.
Okay.
What we are talking about earlier was totally different, right?
Yes. We are talking about different things, but spontaneous symmetry breaking is a statement only about the ground state or vacuum state. That vacuum does not obey the symmetry. Okay. Excited states not obeying the symmetry is not spontaneous symmetry breaking. Okay. So what we were talking about was general spectrum not obeying the symmetry. Whereas if you only restrict yourself to vacuum and vacuum does not obey the symmetry, then you would say it is spontaneously broken. Okay.
So your voice got cut. Can you repeat?
No, I was saying that that whether the entire spectrum becoming a representation of a particular symmetry is different from vacuum not obeying the symmetry. Okay. So spontaneous symmetry breaking is a statement that the vacuum does not have does not preserve a particular symmetry. Okay. Is it audible?
Okay. Yes, sir.
Yeah. So it's like, imagine you write down Lorentz invariant Lagrangian, and then you find a vacuum which does not obey Lorentz invariance. Okay. Then you would say that the Lorentz invariance is spontaneously broken. Because then what happens is that every computation that you do is done in the background of that vacuum, and that vacuum itself does not obey a particular symmetry. Okay. So you'll have to keep kind of correcting for every calculation. So although your Lagrangian did have that symmetry, your state in which you are doing all the computation actually does not preserve that symmetry. Okay. Thankfully, that doesn't happen with Lorentz symmetry, but I just gave that as an example. Okay. Yeah.
Okay, sir.
Okay. Okay. So what we are going to do is to look at these the total Hamiltonian, including the nuclear magnetic moment effects, into 3 pieces, and we will kind of manipulate them one at a time. Okay. Eventually, we'll combine H1 and H2 into a single perturbation piece, but the reason why they are written separately because we are going to deal with these 2 pieces independently first. Okay. So some amount of massaging is required. Okay. So let's start with H1. Okay. So H1 is given by, so there are like bunch of equations really. So we'll just run through one after, in a step-by-step fashion. Okay, so the expression is really minus I e by m times a dot del. That is a piece. Okay, minus IE by m times a dot del. Okay, so that of course in component form is just ak times d partial k. Okay, but ak is something we know. Okay, so maybe I can just click the screen and my computer is kind of ancient, so it is going to kind of takes a lot of time to open anything. Okay, just yeah. Okay, so here's the thing. Okay, so what we do is we write down AK as maybe I've written it down in a component form also. Just hold on. No. Yeah, here. Okay, so we just substitute this one. This minus sign, of course, takes care of that minus sign. Epsilon KLM MNL del M acting on this quantity. Okay. Fine. So del M acting on 1 over R gives you this expression, and partial K is sitting on the right. Okay. Is that fine? So what we'll do is we'll basically just manipulate this expression again. We just push this minus sign and I inside this, write down minus I del K, and the entire expression is written as it is. Okay. But now you see that minus I del K is same as the momentum Pk, and then you have epsilon L mk xm pk. Okay, but that is like the orbital angular momentum. Okay, so therefore we write this entire expression. Remember, L is an index on Mn. Okay, but epsilon L mk xm pk is like orbital angular momentum capital L. So what we will write therefore is that we have a factor E by M, and then we have a R cube factor. So we just pull that whole thing out, E by M times R cube times Mn L times capital LL. Okay, which is just a dot product between the nuclear magnetic moment and electronic angular moment, orbital angular momentum. Okay, you can pull that expression also out by writing Mn in terms of the nuclear angular momentum, and therefore you get a GL times mu n times E by M times R cube, and whole thing is multiplied by I dot L, where I is a nuclear angular momentum and L is a electronic angular moment, orbital angular momentum. Okay, so are you with me with this manipulation? So all we have done is substituted AK and then did some massaging of this expression and showing that the terms that are involved are basically the orbital angular momentum terms of the electron. Okay, and therefore H1, which was minus I by E minus IE by M times A dot del, is actually just nuclear magnetic moment factors times E by mr cube times I dot L term. Okay. Is that fine? So this gives us the interaction between the nuclear spin and electronic orbital angular momentum. Okay, so that is the term. Okay, now let us look at H2. Okay, I hope this is fine with all of you. Okay, just bunch of equations, but one can follow them in a step-by-step fashion. Okay, in case you have any question, please ask. Okay, we can go over this again if required. Okay, good. So let's go to H2, and H2 is this expression. Okay, so let's kind of go back and look at this. E by m times b dot s. Okay, or kind of del cross a dot s. Okay, same thing. Okay, so here is the thing. Now we are again going to substitute a to be this expression. Okay, so we have to take a curl of this expression minus mn cross gradient acting on 1 over r. Okay, so there is a triple cross product. Okay, so we can write out these terms explicitly. So first let's write out this expression. Okay, and you can see that this entire stuff is dotted with s. Okay, so this this double cross product that we have, not triple cross product, maybe whatever. Okay, so this cross product term should have effective index same as whatever is the index that s has. Okay, so if s has an index k, then epsilon should have an index k, and lm should be summed over inside this cross product. So there's a term which is del L, and then this entire bracket has to have an index m, okay, which is written out here. I have not opened this cross product yet. I have just opened this cross product and written down epsilon k L m del L, this parenthesis m, and this k has to contact with this s because this whole stuff is dotted with s. Okay, fine. Now let's open the cross product inside the bracket. Okay, so that gives us, so it has to have an index m hanging around. Rest all indices should be summed. So it is epsilon m, mn carries index n, and this object carries index p. Okay, so this is a del p of 1 over r. Okay, so now you can pull the epsilon out because this derivative is not going to act on that. Okay, so you take epsilon outside. This derivative is not going to act on mn because mn is a nuclear variable written in terms of nuclear variables, whereas this derivative is the electronic derivative. So it just goes in and hits 1 over r. Okay, so what you get is a term like this: epsilon k L m, epsilon m n p, s k, m n n, and del L del P acting on 1 over R. Okay, are you with me on this?
Would you scroll a little?
Yeah.
Up.
Up. Yeah, just hold on. Huh?
Yeah.
Yeah. Maybe I can close the lower window for the time being.
Yeah.
Yeah. So maybe you can see the whole thing at one go. Yeah.
So there's a delta function coming here from 1 by r.
Yeah, yeah. We have a lot of terms coming there, so we will see them. Okay.
Yeah.
Okay. So should I go ahead?
Yeah.
Okay. So now, as Harshit was saying, there would be a delta function coming around. So let's see what happens. Okay. So first thing that we will do is manipulate these two epsilons. Okay. These two epsilons have one index common, which is namely m. So that means there is a epsilon tensor identity which will tell you that this KLs and NP must be related to each other in a particular fashion, and that is this identity. Epsilon KLM, epsilon MNP is delta KN delta LP minus delta KP delta LN. Okay, that is the relation. Okay, so what we'll do is we'll replace these products of two epsilons by these two product of these two deltas and subtraction of the terms. Okay, so once you do that, then you can see that this delta LP piece tells you that this is going to become Laplacian. Okay, whereas this delta function tells you that this is not a Laplacian. Okay, so in one case you get a Laplacian, in another case you don't. Okay, fine. So what we'll do is we'll just kind of substitute that and take it at face value and just compute whatever it gives. Okay. So the first term, as I said, would give you a Laplacian, and it tells you that the delta Kn tells you that Sk and Mn have the same index. Okay, so therefore this is a dot product of S with Mn, that is this term, and delta Lp tells you that del L del P is like a Laplacian acting on 1 over R. Okay, so this is the quantity which is going to give you a delta function. Okay, but hold on to it right now. That is the next step. Then there is a term which tells you that K should be equal to P and N should be equal to L. Okay, so that is this expression, Sk del K Mn L del L acting on 1 over R. Okay, so of course the first term is delta function. That is something we know up to some normalization which is minus 4 pi. Okay, and so that is what we will substitute. What we need to do is to ask what happens to the second term. Okay, fine. Now let's look at the second term carefully. Now notice one thing, that in the first term, because of this delta Lp, we knew that this del L del P is going to give you a Laplacian, and then the Laplacian acting on 1 over R would give you the delta function. Okay. On the other hand, this term has no such rule. Okay, there is a del L del K acting on 1 over R, and we need to kind of look at these terms individually. So one possibility is that when L is equal to K. Okay, so if you have L is equal to K, then this is again a Laplacian, right? And when this is a Laplacian, then it again gives you a delta function. Okay, but when L is not equal to K, then there is no direct guidance, like, there is no such equation which will help us simplify this expression. So in that case, what we'll do is we'll just take L and K acting on this 1 over R and write down that derivative. Okay, so far we haven't been acting any derivative on anything and computing. So this is one place where we actually act and just compute. Okay, so here is the expression. Okay, so when del L del K acts on 1 over R, then you can get one possibility, which is L is equal to K, that is delta Lk, and in that case, just give me a second. So when L is equal to K, then you get a delta function, but we don't know what is the coefficient of that delta function. So let's write down that to be just some number C. We will determine this number in a moment. Okay, and the other piece is when L is not equal to K, and when L is not equal to K, these two derivatives are going to act on 1 over R. Okay, so let's just compute that. When it acts on 1 over R, there are two ways it could act on 1 over R. Once it acts on 1 over R, it gives you some X in the numerator. Second time it again acts on this denominator piece, it gives you one more X in the numerator. The other possibility is that once it acts on the 1 over R, you get a quantity in the numerator. Then the second time the quantity actually acts on the quantity in the numerator, and it gives you a delta Lk. Okay, so that's so. And remember, 1 over R derivative is 1 over R cube actually, because we are taking Cartesian derivatives of a radial variable. Okay, so you can check that it jumps in odd powers. Okay, so this is the expression when del L del K acts on 1 over R when L is not equal to K. Okay, now it may appear that, like, you get a delta Lk here, but this delta Lk has a job of ensuring that whenever this quantity has L is equal to K, it actually should just cancel out. Okay, fine. So first thing that we want to check is that suppose you set L is equal to K, okay, and then you sum over K, then what happens? Okay, so when you set L is equal to K, then this is a Laplacian acting on 1 over R, okay, and that on the left hand side, and that is something we know. That would give us minus 4 pi times delta Theorem-Michel delta function, which is what this expression is, right? So the left hand side tells us that you would get this expression to be minus 4 pi times delta function if you set L is equal to K and sum over all K's. Okay, summing over all K is required because otherwise you wouldn't get a Laplacian. Okay. Fine. Now let's set L is equal to K on the right hand side and sum over K. Okay. So if you do that, then if you set L is equal to K here and sum over K, it gives you a factor of 3 because K takes 3 values. So you get 3 times C times delta function. And when you set L is equal to K here, then you get R squared out here, and L is equal to K gives you 3 here. Okay. That expression just cancels out. Okay. So that is just as well because this expression has come out of this manipulation when L was not equal to K. So whenever you set L is equal to K, this expression should have vanished, and it does. Okay. So what it tells us is that the right hand side of this expression, okay, is given by 3 times C times delta function. Okay. Whereas the left hand side is given by minus 4 pi times delta function. Okay. That pretty much derives C for us. That is given by minus 4 pi by 3. Okay. So we have figured out what this expression is. This is minus 4 pi by 3 delta Lk times the delta function plus 3 times Lxk upon r to the phi minus delta Lk upon r cube. Okay, that is the total expression. Okay, it's written out here. Is that okay? Hello?
Yeah.
Yeah, okay. I'm always worried about not being connected actually. Okay, so what we'll do now is that we will take this expression and put it back into the expression that we had. Okay, remember this, why did we manipulate this one? Because H2 contains this term out here. H2 had 2 pieces. First piece was easy because this was just the delta function. Okay, second piece was relatively difficult, but we have just completed that manipulation. We'll just plug it up here. Okay, so let's write down the entire expression now. Okay, so now remember that we also have to substitute Mn is equal to GL times mu n times the nuclear angular momentum. So the first term that we had was a delta function 4 pi factor GL times mu n times S dotted with the nuclear angular momentum. That is the first term. The second term comes with minus 4 pi by 3 times E by M times the delta function times GL mu n times S dot I. Okay. The last term, which is this term, okay, is again E times GL mu n upon M times R cube. Okay, these were the factors sitting around outside. Then you get 3 upon R squared. Since I have pulled R cube outside, there's R squared sitting around here. 3 upon R squared. And now you check the expression, maybe. Here, okay. So now you check that S has an index K and M has index L. Okay. So therefore, XL will go with I, okay, because that will go with Mn, and Mn is same as I. Okay, so there is a dot product of R with I, and there is a dot product of R with S. Okay, so you get S dot R times I dot R from the top first term, and last term is delta Lk, but delta Lk again tells you that it is S dot I. Okay, fine. So your total Hamiltonian is written as a delta function piece, and then there's another delta function piece, and then there's a dot product of S and I with R or with itself. Okay, so you can kind of rearrange this piece. This is 4 pi minus 4 pi by 3, which is 8 pi by 3 times these two terms can be just added, and you can write down this expression. And the last piece, which is the term in the second row, which is written out here just like that. Okay, is that fine? it okay?
So here it is not easy to directly see what kind of term would it be. Like, is it kind of a repulsive potential or
Which one?
this H2? Like the first term is kind of repulsive because
Yeah,
it's a positive term, and if like S and I are aligned in same direction, they should be like it should be acting as a repulsive term.
that
But
is right. But it's a delta function term, so it is only
yeah, so
acting
it
at
acts only at the center.
at the center. Yeah.
Yeah. So, but the second term is kind of
Yeah, yeah. So second term depends upon which value takes a larger uh, magnitude, decides whether it is positive or negative,
yeah.
right? So if this quantity is larger, then it is attractive piece. If this quantity is larger, then it's repulsive piece. Okay, so depending upon uh, different uh, values, you get different answers. Okay, in our case, of course, things are going to be easy because in our case, not only that I is fixed quantity, which is whatever is a nuclear spin, but S is also a fixed quantity, which is half. Okay, so this expression is either positive or negative. It's not like much of a play there. Okay,
Okay.
fine. So now, having obtained H1 and H2, we can combine these pieces and write down the delta H, which is a combination of both perturbation terms, which is H1 and H2. Okay, so let's write down the terms uh, in a systematic fashion. So let me kind of take this down again. Okay, so I'm writing down this term first. Okay, E by m times 8 pi by 3 delta cube times GL mu n times S dot I. Okay, that is the first term which is coming from H2. Okay, and then there is a term like this. Okay, which contains S dot I piece, and then there is a term which is like this. Okay, so that is combined with H1. H1 contained a term which is I dot L. Okay, let's kind of scroll back and see it again. It was a I dot L piece, E upon mr cube, GL mu n. Okay, so if you go down and see E upon mr cube times GL mu n is a factor common to these both the terms. Okay, so you can write that as I dotted with L minus S because of this minus sign plus 3 upon R squared times R, which is dotted with I, times S dot R. Okay, so that is the expression. Okay, so this is the total perturbation Hamiltonian. Okay, so notice that this perturbation Hamiltonian contains variety of terms. One of them is a term which goes as 1 over R cube. Then there's a term which goes as 1 over R to the 5. And then there's a term which goes as delta function. Okay, and all these terms seems to be divergent terms in the Hamiltonian, and you may have to ask the question that like how come with such divergent terms how do we get finite answers? Okay, and how is it like going to this may badly affect the electronic energy levels? Okay, but the reason why we actually get terms of these kind is because we have included the nuclear spin degree of freedom, but we have not included the finite size of the nucleus yet in our calculation. We're still considering it as a point-like object, and that is the reason why you get a delta function or 1 over R through some arbitrary kind of power terms. Okay, so that is the source of the problem. Okay, and that is the reason why we get this. Now, this class of approximations are fine, and we could kind of continue using this kind of Hamiltonian, provided electron spends most of its time far away from the nucleus. Okay, if electron is actually in the close vicinity of the nucleus, then this point particle approximation of the nucleus is not correct, and in that case you will have to kind of revisit this problem and in fact abandon this kind of expansion and do a finite size correction of the nucleus to the electronic problem. Okay, so the approach that we we are going to take is to assume that electron spends most of its time away from the nucleus, take this formula, compute, check with the experiment. Okay, if they agree with the experiment, then our assumption is right, that electron spends most of its time away from the nucleus, and therefore we just continue working with this. If it fails miserably, then we just abandon this program and first include the finite size nuclear size correction effects and then compute the quantities. Okay, that's fine. So is a kind of practical approach that we will basically say that if the answers are correct, then that means if they agree with the experimental data, then we would say we are doing fine. Okay, if not, we'll kind of revisit the problem. Okay, is that fine?
Yeah.
Okay, so now that we have obtained the perturbation Hamiltonian, okay, which is this term plus this term, we could ask a question that like, okay, what is the correction generated by this Hamiltonian to electronic states? Okay, now of course we can study that, but before we study that, we have to notice one thing that electronic states are actually degenerate. Okay, it is 2 times 2j plus 1 fold degenerate for j less than n minus 3 half, and it is 2j plus 1 fold degenerate when j is equal to n minus half. Okay, so therefore, when you want to treat delta H in perturbation theory, then we actually have to solve degenerate perturbation theory problem. Okay, so we not only have to kind of use the new Hamiltonian, but we have to actually solve degenerate perturbation theory problem first. Okay. Okay. So of course, if you have to solve this problem, you need to choose a suitable basis in which you can solve this problem. And to do that, we will follow the same thing that we did in the hydrogen atom problem. Namely, we write down a new angular momentum J in which is L plus S, and then change the basis from LS ML basis to LS JM basis, and compute relevant quantities that we want to compute with respect to the total electronic angular momentum. Okay, which is what we call J. Okay. Now, in this particular case, we want to write down a total angular momentum for the combined electron nuclear system. Okay, and which we will call F. Okay, and F is I plus J, where J is of course L plus S. Okay, and what we want to do is to understand how we would use F to compute the spectrum, or to write down the spectrum in terms of F and its magnetic projections, which will be called MF. Okay, fine. So that is what I was just saying, that we will work in the eigenbasis of F and Fz. Okay, good. So this is equivalent to the same statement, which is related to the statement that I just made about L plus S thing, that you initially had a LS ML MS basis and you will go to LS JM basis. We will do the same stuff here. We will start with the basis which is NLS equals half JMJ basis, okay, which is already a basis in which ML MS pieces have been combined into JM basis, okay. But our total basis is this tensored with the nuclear basis, which is IMI, okay, and we go from this basis to a new basis, which is NLS equals half JIFMF, okay. So our states are written with respect to huge number of quantum numbers, but effectively what we are going to work with is basis which involves I, J, F, and MF. Okay, or we could work with I, J, MI, MJ. Okay, so that is exactly the way we had worked with in the LS versus J basis. Okay, so what I'll do is that I'll stop at this point, and we will kind of use this new basis. write down the spectrum of states when we consider the perturbation generated by delta H. Okay, but that will be in the next class.
Would you go to the previous slide?
Yes, sure. In this one or one before that? Okay.
Are we going to treat delta H as a perturbation though?
Yes.
We aren't going to solve some exact calculation.
Well, well, we have to solve it in degenerate perturbation theory, right? So we can compute those matrix elements exactly, but in the matrix elements of the perturbation theory problem. For example, delta H will lift certain degeneracies. Okay, we had a 2j plus 1 times 2i plus 1 kind of degeneracy, and it could also additionally have a factor of 2. We will see that that degeneracy will actually be lifted by this Hamiltonian.
Okay.
Okay. Any other question?